now. So hi everyone, I'm Tong from HKUST. So I'm very glad that I can attend this year's SGC 2022. So today my topic is about the large spin-2 signals at the cosmological collider. And this is a work in collaboration with Xianyu Zhongzhi and is based on the following archive paper. So let me begin with a brief introduction of the cosmological collider physics, which has become a rising field in the recent 5 years or so. It's a very interesting idea. So assuming that the early universe is described by a period of inflation where the space-time expands exponentially, and with a Hubble scale up to 10 to the 13 GeV. So this exponential expansion of space-time produces particles spontaneously through the Bogdanov transformation, and these particles can carry an arbitrary mass and spin. So if these particles produced from the space-time expansion couples to the massless curvature perturbations of the universe, then these massless curvature perturbations, denoted as zeta here, will carry the information of the massive particles to the boundary of inflation, namely the end of inflation, which later becomes the temperature perturbations that we see on the CMB sky or in the large scale structure of the universe. Then by looking at the correlation functions of these curvature perturbations and temperature perturbations, we are able to extract valuable information about these particles at the bulk of inflation. So since the Hubble scale of inflation can be very high, so this is a very interesting arena for testing particle physics models. So that's why it's called the cosmological collider. From now on, I will sometimes abbreviate cosmological collider as CC. So if you look at for example, the 4-point correlation functions with certain momenta, external momenta, and you vary the momentum configuration, and you can read out the mass as the oscillation frequency of the momentum ratio. You can also read out the spin of the particle, internal particle, by looking at the angular dependence, PS cosine theta. However, one big challenge of this paradigm is that the overall CC signal strength is suppressed by a Boltzmann factor, because we know that inflation is approximately a quasi-de Sitter space-time with a background temperature of order Hubble. And this makes it very difficult to observe heavy particles, especially for particles with mass larger, for example, 5H. This motivates us to look for mechanisms that amplifies these signals. So the signal strength of the CC comes from the unshelled particle production, because these oscillations are really the propagation, the dynamical phase of particles propagating in inflation. So the signal strength is proportional to the particle number density during inflation of the massive particles. And this is extremely small for the Boltzmann suppression reasons. But what's the reason for this? Yeah, we realize that the secret is about the symmetries. We know that inflation is a quasi-de Sitter space-time with 10 isometries, including 3 translations, 3 rotations, 1 dilation, and 3 de Sitter boosts. And together, they dictate a de Sitter variant particle production rate to only depend on the conformal weight of the particle, which is the mass, and take this following Boltzmann form. But let us recall that inflation is not exactly de Sitter, because the 3 de Sitter boosts are broken spontaneously by the rolling inflaton phi dot. So that provides us a solution for this amplification problem, because if we couple the rolling inflator background to the massive particle sector, we may be able to alleviate this Boltzmann suppression. And such amplification is possible via something called a chemical potential. So what is a chemical potential? In statistical mechanics, we know that the chemical potential is given as the Lagrange multiplier of the particle number in a grand canonical ensemble. If we go to field theory, we invoke locality as well as Lorentz covariance. We can adapt this same chemical potential term to field theory, which is a local operator in the Lagrangian that takes the form kappa mu times J mu. J mu is the analog of the n particle number n here. It's a matter current, and kappa mu will be the analog of chemical potential. This chemical potential is usually provided by a background field, for instance, the rolling speed of the inflaton background. So the physical picture is also quite simple. So you have a rolling inflaton background rolling off the hill, and this rolling speed provides, this breaks the de Sitter boost and alleviates the Boltzmann suppression, and on its trail, lots of massive particles are produced, which can be used later for cosmological collider purposes. The chemical potential of massive lower spin particles are well studied in the literature. For instance, the spin 0 particle has a chemical potential which corresponds to the Schwinger effect. And for spin 1/2 particles, this is the actual current. And for spin 1, massive spin 1, this is the Chern-Simons term in the Lagrangian. And in all these scenarios, it is known that a resultant CC signal receive huge amplifications from the chemical potential, where the signal size is boosted from this Boltzmann term to this e to the minus pi m minus kappa, where kappa is the chemical potential and m is the mass. So you see, this is really an exponential amplification of the signal. So that's okay for lower spins, but how about higher spins? In particular, the case of spin equals to 2. And let us be reminded that inflation is a very high energy process, and it may not be that far away from the gut or the closer climb of the string scale. So there are actually ample motivations for studying those spin-2, massive spin-2 particles during inflation. For example, it can come from the KK gravitons from the gut, or it can come from the famous open string spectrum. So we need to also find a way to amplify those massive spin-2 particles via introducing a chemical potential. That's our goal. So we need a spin-2 chemical potential. What ingredient do we need? So we need an EFT operator with the lowest possible dimension, because we are working in a field theory language. So everything should be local, added in the Lagrangian. Yeah, and second, it has to take the form of this chemical potential, kappa mu times J mu. Otherwise, it wouldn't be called a chemical potential. Third, it has to be quadratic in the massive spin-2 field, so that it can contribute to the linear equation of motion. Fourth, it should break de Sitter boost, keeping the rotations, translations, and dilations invariant. So this is one of the necessary conditions I mentioned before, symmetry breaking. And last, it should give rise to a consistent ghost-free theory in the IR. So these are the 5 constraints that we pose. And by considering these conditions, we single out a unique spin-2 chemical potential that takes the following form. Here, phi is the background inflaton field. Lambda c is a certain cutoff from the UV theory. And then epsilon is the 4-dimensional Levi-Civita tensor. And these H's are the massive spin-2 fields. And they are coupled in this kind of a way. So this will be our spin-2 chemical potential term. And we add it to the Lagrangian to see its effect. Let's first study the linear theory. So the linear theory consists of the usual Einstein-Hilbert term, which is basically the kinetic term in the linear regime. And the mass will be provided by a fierce Pauli mass tuning. And last, this is our new ingredient, which is the chemical potential operator we introduced in the previous slide. And we define this kappa to be the rolling speed phi naught dot divided by the UV cutoff lambda c. So this is our linear theory. Phi is here provided as a background field, so we don't take its fluctuations into account. It's just a background field. It has a time dependence in it because it's rolling. If you vary this action with respect to the spin-2 field, you get its equation motions and all of its usual 5 constraints, the transverse traceless conditions. You can see the equation in the equation of motion, the first 2 terms correspond to the usual Klein-Gordon form, where the last term is the effect of the chemical potential. Naively looking at this set of equation of motions and constraints, one would guess that the degrees of freedom for this theory would be 10 minus the 5 constraints equals to 5, which is somehow matches our intuition from the little group analysis in the flat space time. However, what we have found is that after you expand this H mu nu in terms of its helicity components, 5 helicity components, there's a non-local constraint that kills all the vector modes. This is an algebraic equation that requires that the helicity plus minus 1 modes vanish. So this effectively reduces the degree of freedom to 3. And after removing the vector modes, the remaining theory is goes free, and one can go on and solve its equation of motions, solve its mode functions, expand them in a late time limit to obtain the Bogoliubov coefficients, and hence the particle production number density. And the result is that in the large mass limit, the particle numbers has this kind of spectrum. As we can see, the helicity plus minus 1 modes are killed by the constraint, so they don't appear. But the helicity plus minus 2 modes are affected by the chemical potential. In particular, the original Boltzmann form is shifted linearly by the chemical potential, 1 plus kappa, 1 minus kappa. So the helicity minus 2 modes are exponentially enhanced, while the helicity plus 2 modes are exponentially suppressed. The longitudinal mode is completely unaffected by the chemical potential. So, so we see that these helicity minus 2 modes are exponentially enhanced, so which will give rise to large CC signals. That's parity violating because of this asymmetry between the helicities. Now, now we have prepared ourselves a group of massive particles produced from the chemical potential. Then we need to couple them to the visible sector, namely the inflatons and the gravitons, which is the tensor perturbations you see on the B modes of the CMBs. They can be easily coupled via these 2 operators in the EFT over inflation. They're all dimension 5 and they're all symmetric under inflaton shifts. And they are not invariant under the speed-2 gauge transformation and time diffeomorphism. So this means some constraint will be posed in order to ensure the EFT validity. So after turning on these couplings, one can observe the effects of the spin-2 particles enhanced by chemical potential by looking at the following correlators. For example, the curvature tensor bispectrum, mixed bispectrum. There's a tree level diagram like this. The blue line corresponds to tensor modes, gravitons, while the black lines correspond to the inflatons. And you can also look at it in the 4-point functions. So because of time reasons, I will only discuss summarize a few interesting features in the observables. Um, First of all, let's look at the 3-point function, gamma, zeta, zeta, gamma, this first diagram here. So in the soft limit, we see these oscillations in the momentum ratio, where K1 is one of the external inflaton mode, and the K3 is the external graviton mode. So these oscillations are these CC signals that I mentioned before, and their frequency characterizes the mass of the internal particle. So the amplitude is amplified because of the chemical potential. But this is done in a helicity dependent way, a parity violating way because of the chemical potential. So the -2 helicity modes gets enhanced. So you see these larger oscillation amplitudes, but the +2 helicities modes, these modes have a very small oscillation amplitudes. This is precisely because of their difference in the particle occupation number. So this is a kind of a parity invariant, a parity violating signature. This is also manifested in the angular dependence, where you fix the size of the momenta but vary the angle between them. You see that for this yellow line is the +2 helicity mode, while the blue lines correspond to the -2 helicity modes. With a larger chemical potential, the overall amplitude also becomes greater. At the tri-spectrum level, namely the 4-point correlation function of the curvature perturbations, there's also something interesting called, namely that the 4-point function will grow a non-perturbatively small imaginary part because of the parity violation. So it's manifested as the odd dependence on the dihedral angle spanned by the 2 pairs of the momenta. So this is the odd function of the dihedral angle. So it's actually an analogy of the decay-plane correlation in particle physics. So this imaginary part is non-perturbative because it's suppressed by e to the minus pi mu factor, where mu is the mass of the particle. So you cannot see this in at any order in the large mass EFT expansion. So it's intrinsically non-perturbative, and it comes from real particle, on-shell particle production and propagation. After all these interesting features, can we see them via future experiments? And the answer is yes. So here we plot the parameter space feasible for future CMB and 21 centimeter observations. The horizontal axis correspond to the chemical potential in units of Hubble. The vertical axis correspond to the mass of the spin-2 particle. And the gray regions are excluded, and the colored regions can be probed via light birds as well as futuristic 21 centimeter observations. So as you can see, even if we choose something, some mass as large as 15 units of Hubble, we can still observe some for a non-zero kappa. This is the magic of the chemical potential. We can see them even if the spin-2 particles are very heavy. Yeah, so let's come to the conclusion part. We started with a brief review of the cosmological collider physics, and we identified the challenge in the paradigm, which is the signal suppression. And then we found out the reason is because of the part of the reason is because of the symmetry. You see the symmetries which we must violate, and we introduced the chemical potential to do so, and we generalized these chemical potentials from lower spins to spin-2 case, which is interesting in itself. And then we look at the observables in this model that can be probed by future experiments such as Lightbird or 21 centimeter experiments. And there are also a few outlooks, mainly about the model itself, that like we can consider non-perturbative mixings, as well as the apparent discontinuity and the degree of freedom count. Also, we are studying exclusively in the EFT regime. We need to perhaps look at the UV completions for these models. And then we need to go beyond spin-2, which is interesting because it may be also, it may help us to probe the rigid trajectory if we can see the string oscillatory modes. So that's all for my talk. Thank you very much for listening.
Thank you. Any question or comment?
Hello, I have a question.
Yes.
Okay. At first, what is scale for your mass term?
Oh, the mass term. You mean the mass of the spin-2 particle?
Yes.
Oh, so it's something greater than Hubble. So actually, in this figure, so the vertical axis is the mass of the spin-2 particle. So it can be like 15 Hubble or 5 Hubble or something like that. But okay, it has to be greater than 1.5 Hubble.
Okay, because you mentioned that you want to study study spin-2 respect to from the string theory. So I guess
yes,
the mass should be proportional to one of our prime.
Yes.
Not the Hubble. Because if you use the string theory to derive the spin-2 particle, then mass term should be proportional to one of our prime.
Right. So because the string scale is not precisely known, it could be around a little bit higher than Hubble. So if you rewrite this mu as n over alpha prime, a square root of n times 1 over alpha prime, then it's possible that we can see the string structure.
Yeah, but how do you see that from the experiment? If it's alpha prime.
Well, if alpha prime is not that, well, if the string scale is low enough, you can see it because the mass in our model is a free parameter. So you can measure to the string mass.
Okay, maybe okay, because it's free parameter, you can set any scale. But somehow we expect, okay, let me ask a second question.
Yeah.
Do you have a nonlinear extension for your theory?
Yeah, so that's actually one of our outlooks. So we need to look for the UV completions for this model because actually in the degree of freedom count it's kind of mysterious. So even if the chemical potential is vanished, I mean, tend to 0 continuously, there is still a discontinuous degree of freedom count. So there seems to be something similar to the VDVZ discontinuity in massive gravity. But there, the problem is resolved by looking at the nonlinear regime, resumming the higher orders. But
we are no ghost problem is problematic due to the nonlinear extension, not due to the quadratic. So for the quadratic, therefore, it's easy to get a ghost-free theory.
Right.
Yeah. So. Right.
So here in this work, we just treat them as the EFT operators. So we do not we haven't looked into the nonlinear theory more carefully, but actually, so there are, let me see. Yeah, so there are some model in the literature called the Axion SU2 model, which probably can serve as one possible UV completions for our model. But in that case, the SU2 particle is an emergent state from the condensation of the axion.
Okay, if I do not misunderstand their model, they need to consider the other fields other than the spin-2.
Right, their spin-2 is an emergent particle. So they actually come from the SU2 vector gauge bosons. Yeah.
Not just spin-2, you also need to consider other matter field to have a
yeah.
Otherwise, you cannot have the ghost-free.
Right, possible.
Okay.
Yeah.
Okay, thank you. I understand.
Yeah.
Okay, let's thanks the speaker.